Welcome to Logical Verification 2020 to 2021. This video is about Chapter 12, Section 3, Coercions. In Lean, it's sometimes the case that you have a natural number and you want to use it where an integer is expected. Now, the natural numbers and the integers are two different types. They are not equal, and hence you cannot use a natural number directly as an integer. One solution would be to use a function like net.toInt, but this gets old really quick. Whenever you have a natural number and you want to use it as an integer, you'd have to write a long function. You don't want to do this. Instead, Lean has a nice mechanism called coercions, where whenever you want to use a natural number or really anything, any element, in place where a different type is expected, Lean will insert a so-called coercion, which transforms the stuff you have to the stuff that is expected. For example, transforms a natural number to an integer or an integer to a rational number. So, coercions are implemented in type classes in Lean. The type class has coe, and if you provide an instance of this, for example, has coe from string to list of characters, then you can extend this coercion mechanism as much as you want. And this type class has one operation, namely has coe AB, has a function from A to B. Right. So for example, if we in this lemma here, if we have here two arguments, one is a natural number n, and the other one is an integer z, and we want to multiply them together. This happens quite often, as you might imagine, but if you recall, the multiplication is an operation from alpha to alpha to alpha. You cannot multiply a natural number with an integer. And so you need to convert the natural number to an integer first, and then multiply them together. But since we have coercions, we do not need to write this coercion out when writing the lemma statement. Instead, we can just write z times n. What Lean will do is it will implicitly insert this coercion when you write this. So when you have an n, and when you have a natural number where an integer would be expected, Lean will insert the coe function, which is then rendered as this wonderful up arrow. Now, quite often you want to know, like, what is this up arrow exactly, and what types does it coerce between. The easiest way to figure this out is to click on this here and see that it is in coercion between natural numbers and integers. Okay. Another important detail that we will probably run into very quickly is what happens if you do it the other way around. Okay, this actually works. So what happens if you do this in the wrong order? So how Lean inserts coercion is extremely dependent on the order you write terms in. So if you write here the natural number first, instead of it would work just fine if we had c times n, but it does not work if you have n times c. And this depends on the order. So because when Lean sees the n, it hasn't seen an integer first, so it doesn't know that it needs to coerce it somewhere. While if it sees the integer first, it knows, oh, we're now looking for integers, and if it after seeing an integer sees the natural number, then it will know, okay, the types are different, I need to coerce them. So the typical solution in this case here is a type annotation, where you tell Lean, okay, I expect an integer here, make it match. Okay. Yes. So this works in many situations. Now, the way you prove things about coercions, well, the way, very nice, convenient tactic when you want to prove things about coercions is the normcast tactic, which tries to simplify coercions in a useful way. So for example, if you have an equality between two coercions here, so like up arrow equals up arrow, then normcast will typically be able to remove this one. So this knowledge that you can remove the up arrow here is not built into normcast. This works by annotating lemmas with the normcast attribute. So if you want to have your own types with coercions on them, and you want normcast to work on it, you need to tag the lemmas using the normcast attribute. Okay, right. So normcast can do quite a lot of things. Another interesting one is this here. You won't see what it does. So in many cases, normcast can actually close the current goal. For example, if it can simplify it so that both sides of the equation are the same, but it can also return a simplified version. So for example, if we just make it 0 here, then just like the simplifier, it will end with the simplified goal. So right, we start with 0 equals up arrow, m plus n, and then, okay, this is again not particularly helpful probably. Right. Anyhow, so you will get the simplified result even if normcast cannot close the goal.